So hi everybody, welcome to the third invited talk of the conference, which is the Test of Time Award talk, as traditional in TCC. So I'm on behalf of the Test of Time Award committee, which is Mihir Belar, Rafael Paz, and myself. It is a somewhat bittersweet pleasure to give the Test of Time Award 2044 to the paper Notions of Reducibility Between Cryptographic Primitives by Omer Reingold, Luca Trevisan, and Salil Vadhan, which was presented at the first TCC 2004. And the citation reads, for providing rigorous and systematic taxonomy of reductions in cryptography, in particular coining fully black box reductions and motivating their use in barrier results. It is very sad that Luca is no longer with us to savor the award in person, but I'm certain that he is severed in spirit. So before giving the award to Salil, let me say a few words about Salil. He was graduated from MIT in 1999. That he's since then been a professor at Harvard University, the Vicky Joseph Professor of Computer Science and Applied Mathematics. And he's been managing to have three parallel successful lives in foundational cryptography, pseudorandom complexity, and in societal aspects of data science, in particular differential privacy, fairness, calibration, and things that are really the most applied, the most user-oriented, and are having a lot of impact on the world. And somehow he's managed to combine all the three, and today I think we're going to hear back to crypto from understanding or wisdom that was arrived in the other two areas. So without further ado, let me award the Test of Time Award to Salil.
Okay, thank you, Ran, for the very generous introduction into the committee. It really means so much to Omer and me receiving this, both because of this really amazing community and conference that's so near and dear to our hearts and was such a big part of our careers, and coming back here to TCC, attending in person for first time in a number of years, I really feel like I'm coming home. And also and especially to receive it together with Luca here at Bocconi at a time when we're mourning the loss of him, but celebrating his life and all that he gave us. And as Ran said, I only wish he was here to enjoy this moment with us. But we'll settle for the fond memories it brings back for us. And so, yeah, starting with this photo, which is from 2004, the year of the award. I have a little bit more hair back then. But Luca basically looks the same as he did a year ago. And you can see him looking skeptically at what toppings they were putting on pizzas in Cambridge, Massachusetts. So that was really a magical time period for the three of us. It was the most intense period of both our collaboration and our friendship, with those two things totally intertwined and growing in tandem. Many fond memories of both scientific and personal discussions, and debating over drinks late at night on why we do what we do. Is it because it's important? Is it because it's useful? Is it because it's fun? The only thing we could agree on was that it's that the subject, theoretical computer science, is beautiful. And that was, we toasted to that and ended the debate. We had this one of these U.S.-Israel BSF grants, 2 of them in sequence during that time period. It was kind of, sort of like a trivial amount of money for people. I don't know if it's still the case, but but somehow was nice for us in kind of just continually reminding us that we want to be spending time together and working together. And so it was also, one of the reviewers, I think, complained and said, shouldn't give them the grant because they're going to work together regardless of whether you give them this grant or not. But we found it kind of useful as a prompt, and I listed here the papers that the 3 of us, this one, the TCC 2004 paper, was our first paper of the 3 of us co-authored, and then we had a number of others, and then many more with pairwise collaborations. In this talk, I will only say a little bit. I have one slide on black box separations and reductions, in part because it's not an area that I've kind of continued working in a whole lot over the time period, and I feel like talking about a line of work that really, I think, originates with this 2008 paper, Dense Subsets of Pseudorandom Sets. I have some more new and kind of things to say that might be useful or spark some things for you all. So that's where I'll spend most of my time. But let me start with this 2004 paper. We had been having a number of discussions of trying to understand. There was, kind of emerging set of black box separations. There was in Pagliazzo-Rudich, which I'm sure people are familiar with, but then there was also the lower bounds on efficiency, Gennaro, Gertner, Katz, Trevisan, which was kind of doing things in a different way. And we mostly, were spending time just trying to make sense of it for ourselves. We were confused about what they mean by black box reduction. Is it the same thing that they mean by black box reduction? Are the barriers telling us the same things? And so, but it was unclear whether we were ever actually going to write down our kind of thoughts on this until the conference TCC was created, and it was that's the perfect venue. There's an audience, that'll be the community of people who will actually, it makes sense to share these ideas with. And it didn't make sense in the kind of crypto conferences prior to that, really. Or even the complexity ones were a little bit more structural complexity focused. So TCC really sort of fit a niche. And for me, I think that kind of realization made me also more welcoming of TCC as a conference, because I was worried that the creation of TCC would kind of cut off the theory of cryptography community from the other adjacent communities that it should be interacting with. I'll say more about that at the end. But I think you can just see from the program this week how much of a value and need there was for a conference like this. So something that we state in the paper, we actually use this phrase, the most glaring open question, is to understand the efficiency and seed length of pseudorandom generator constructions from general one-way functions. Right, so one of the foundational results in cryptography, starting with Hastad and Pagliazzo, Levin, and Luby, really should be 90, not 99. That's I'd like for when the result is from. So here, what efficiency contributes? So we have a one-way function mapping, say, n bits to n bits, and n also will take to be the security parameter. And we construct from it a pseudorandom generator that has some seed length, which is a function of n, L of n. So we care about that in terms of efficiency. It has some stretch S of n, but the 2 main efficiency parameters is the seed length, and then in terms of time efficiency, how many queries does the pseudorandom generator make to the one-way function? And this is still a glaring open question. There's been this long line of work starting after Hill in improving the efficiency of this construction. And the current state of the art, the query complexity is O tilde of n cubed queries to the one-way function, and the seed length is O tilde of n cubed, so cubic in the input length of the one-way function. And what we know in terms of lower bounds for black box constructions is very far from that. So the work of Luca and others that I mentioned earlier on efficiency of cryptographic constructions gives a lower bound that's related to the stretch of the generator, basically the stretch divided by log n. These should be omega tildes here. That lower bound holds even for one-way permutations. And then there's a beautiful lower bound by Hollenstein and Sinha that proves a lower bound of that doesn't. So when the stretch is 1 bit, that or if you're just looking for a non-trivial generator that stretches by 1 bit or log n bits, this lower bound gives you nothing. Hollenstein and Sinha prove that you do need at least nearly linear in n queries to the one-way function, and that holds even for regular one-way functions, as long as you don't know the regularity of the one-way function. And these lower bounds are both tight for these cases of one-way permutations and regular one-way functions. So they're not really getting at the complexity that comes from a general one-way function. And for seed length, we know nothing non-trivial as far as I know. Okay, so I would like to just remind the community of this open problem. I still think it's a great question. I wrote, there's going to be a column in SIGAC News coming out this month, Open Problems in Memory of Luca Trevisan, and I wrote a little write-up of this problem and maybe some thoughts on what should go into a lower bound in case you're interested. And both of these sources of inefficiency, the main source is coming from doing many independent evaluations to convert Shannon entropy into min entropy. Okay, and there are contexts in which we know this kind of, at least that kind of a blow-up, a n-squared blow-up is needed for that, but we don't know how to connect those settings to this setting of one-way functions, pseudorandom generators from one-way functions. All right, so now let me turn to the other, where I want to spend most of the time. This started with this paper of the three of us together with Madhur Tulsiani. And this came in a time where theoretical computer science was starting to import ideas and tools from an area of pure math called arithmetic combinatorics or additive combinatorics. These are kind of related, intersecting areas. There was this beautiful multi-source extractor construction of Barak and Pagliazzo and Vigderson using the sum product theorem in finite fields. There was work of Luca and Alex Samoritsky on PCPs and kind of property testing type questions using the so-called Gowers norms, and then Andre and Emanuele Viola also were using those Gowers norms in analysis of pseudorandom generators for polynomials. These were two flavors. One, here in these extractors, you're using the results from that other field as a black box. Just take the theorem, maybe do some soup up version of it, but you're then using that as a tool for some combinatorial construction. And in these other cases, they were being used in settings where at least the objects we're talking about seem to be of a similar flavor. They're involving something algebraic, polynomials, or multivariate polynomials over finite fields. Really extremely, it's not to dismiss it, very extremely interesting, beautiful applications. But I think Luca suspected there were some deeper connections between the things they were thinking about in those fields and what we think about in complexity theory. Kind of similar to, it was mentioned, his constructor of extractors from pseudorandom generators, really connecting things that seem on the first glance totally unrelated to each other. They shouldn't be related. And in particular, he suspected there was a deeper connection between ideas that we study in complexity theory and things happening in the Green-Tau theorem. So the main Green-Tau theorem is that the kind of celebrated result that the set of prime numbers has arbitrarily long arithmetic progressions in it. The way they prove this, kind of one sort of like intermediate point is to prove that the set of prime numbers in some sense is indistinguishable from another set of natural numbers that has constant density in the natural numbers. Like 1% of the natural numbers, kind of asymptotically as you look at as n goes to infinity. And then you could apply Semiretti's theorem, which says that any subset of the natural numbers that has constant density has arbitrarily long arithmetic progressions, and deduce by indistinguishability that the prime numbers have arbitrarily long arithmetic progressions. And Luca felt that there should be a complexity theoretic analog of statements like this, or the way they get this statement about indistinguishability from a set of constant density. And this is the complexity theoretic dense model theorem, which is the main result of this 2008 paper. Says that if I have a pseudo-random distribution X, and I have an event of some non-negligible probability delta, and I look at my pseudo-random distribution conditioned on this event, all right? And this event can be like arbitrary. It doesn't have to be. The interesting cases where it's not an efficient event. So, I'll mention later the kind of like an example is like in leakage resilient cryptography. E is an event when you condition on some leakage on the seed of the pseudorandom generator, for example. Okay. Then actually your pseudorandom distribution conditioned on the event is actually computationally indistinguishable from some distribution on that has constant density in the uniform distribution. Okay, so let's show a picture. So I have X indistinguishable from the uniform distribution on all of 0, 1 to the n. You can think of X as like, sort of much smaller. We know pseudorandom distributions can be much smaller. There's some event of constant density, and now there exists a dense model of X conditioned on that event. And in the context of Green and Tau, E here is the prime numbers, which have constant density in something called the almost primes. These are numbers with not too many divisors. And it was known that there's a sense in which the almost primes are indistinguishable from kind of the natural numbers as a whole. And by a dense model kind of theorem, they get that there is a subset of the natural numbers as a whole that's indistinguishable from the prime numbers, and they can apply Semiretti's theorem. But to me, at least, it seemed like, okay, yeah, superficially, they're kind of talking about things that are similar to us, but surely there can't be like a direct connection between. But Luca's intuition was right, and we managed to get this complexity theoretic dense model theorem. And soon it was connected. I mean, immediately in the same conference, there was this paper of Christoph and Stefan Zimbowski using dense model theorems for leakage-resilient cryptography. It was realized it was very related to computational notions of entropy that were introduced and studied by Barak, Shaltiel, and Vigderson. You can read, I recommend this paper by Fuller and Raisin for kind of explaining some of those connections, and also very related to Impagliazzo's hardcore lemma. So we had kind of, in our proof of the dense model theorem, had taken ideas from the proof of the hardcore lemma and used that to prove the dense model theorem, and then Impagliazzo showed that you can actually prove the dense model theorem using the hardcore lemma. So there's a whole bunch of things that seem really related, but kind of Luca still was looking for a more, like even deeper unifying principle, and the conjectured answer was that should be some kind of regularity lemma. So what is regularity? The classic example of regularity is Semireti's regularity lemma in graph theory, which says that every graph, an arbitrary graph, no matter how complicated, is indistinguishable from some graph of low complexity that has kind of simple description. A little more precisely, but not with all the details, for every graph, and you give an approximation parameter epsilon, there is a partition of the vertex set of the graph into k pieces, where k is some function of epsilon, depends only on epsilon, doesn't depend on n, the number of vertices in the graph, such that if I look at any pair of those subsets in the partition, like so vi cross vj, and I restrict the graph to the edges there, but in that between those two sets of vertices, that is epsilon indistinguishable in some sense from a random graph, and from a random graph of edge density that matches the edge density of G in that between that pair. So that's just the edges in G. What proportion of them, of the possible edges between that pair, are actually in the graph G. Right? And this holds not for all pairs, but all but an epsilon fraction of pairs, where we weight the pairs by the densities. So like pair ij, we weight by the density of vi times the density of vj. Okay, so this picture is meant to indicate, like, the dark ones are like, okay, G has a high density there. It looks just like a random graph of high density. Here it looks like a random graph of some lower density between that pair, and so on. Importantly, and maybe this was a little bit of a psychological barrier for us, the number of parts in Semireti's theorem is enormous. It depends only on epsilon, not on n. So if epsilon's a constant, it's a constant. But it is a tower of 2's of height polynomial in 1 over epsilon. So 2 to the 2 to the 2 to the 2 to the 2. All right. And in fact, it is known that that's necessary for Semireti's theorem, remarkably. All right. So this seems very bad for complexity theory, because epsilon for us will be like our indistinguishability parameter, like negligible. We can't think of epsilon as 1 over poly or slightly negligible. Can't afford to be paying towers in epsilon. But we did come up with some kind of complexity theoretic regularity lemma in this next paper with Luca and Madhur Tulsiani, which does say in some sense, every Boolean function, again, think of G again as arbitrary, no constraints on its complexity, it's really an arbitrary function, is indistinguishable from some function of low complexity. All right, so I'm given an arbitrary function G, some distribution in the domain, you can think of that as a uniform distribution, a size parameter and an epsilon. There exists a low complexity approximation H, such that H is low complexity in that it's computable by a circuit of size just a little bit bigger than our parameter S. We'll see what other role S plays in a moment, times some polynomial in 1 over epsilon. And second says that H and G are epsilon indistinguishable by all circuits of size S. Okay, so this is the way we wrote it in our paper, kind of also to match the way that people are stating these indistinguishability criteria in the arithmetic combinatorics, because they think of this as an inner product. F is almost orthogonal to the difference between H and G, but a different, maybe more familiar for cryptographers way of saying this. So I wrote H and G here not as Boolean functions. I wrote them as and it's important that H is allowed to be fractional, even if G is Boolean. So we think of these as randomized, as describing randomized functions. So like H rand on X, you can think of as being the randomized function where you're 1 with probability H of X and 0 otherwise. Just by taking expectations, we can replace H and G here with H rand and G rand. It gets the same thing. And with up to an additive constant in the circuit size, this statement is equivalent to saying the joint distribution of x and H rand of x, the randomized function, is computationally indistinguishable between x and G rand of x. And computationally indistinguishable, I'm using the subscript S epsilon by circuits of size S with advantage at most epsilon. Okay, so this is a very kind of more familiar way of writing it. And you may recognize this is the content of the kind of leakage simulation lemma of Kishtov and Jetchev. The leakage simulation lemma also of their paper like optimizes a bunch of parameters that I won't get into. You care about the dependence on epsilon, and this is also only right now for the case of 1-bit leakage, and their leakage simulation lemma handles, like logarithmically many bits of leakage. But just to connect with the things we're talking about, also to things we care about in cryptography. All right, so later in the talk, I'm going to drop these rands and often just write, I'll take G not to be this fractional function, but to be a randomized function. Just for notational simplicity, so I can write most statements in this form. Okay, and we observed in our paper that we showed that from this regularity lemma, you can derive the dense model theorem, you can derive Impallotta's hardcore lemma, but not totally satisfactory. You don't get the optimal result. You don't match Hollenstein's optimal version of the hardcore lemma. And there was maybe a little bit more calculation needed here than ideal. So maybe we weren't quite getting exactly the right formulation of the regularity lemma, but still was very, very useful. And the other point is that I've stated it here for kind of the complexity theoretic version that's also useful in cryptography, but your domain doesn't have to be bit strings. It can be an arbitrary domain, and your family of distinguishers doesn't need to be circuits. It can be any family of functions on your domain. And then the only thing that changes is that what does it mean for H to be low complexity? It means that it's obtained by combining a small number of functions from your class. Right? So you have F1, Fk are in your family of distinguishers, and there exists k of them, poly 1 over epsilon of them, that I can combine, and I can in fact combine them using a circuit of size poly 1 over epsilon. And that will be what this easiness condition of H, low complexity condition of H, gets replaced by. And then once you formulate it this way, you can do a graph theoretic interpretation by taking X to be, you're thinking of graphs on n vertices, you take script X here to be the space of possible edges in your graph, right? For every element of n choose 2, you have a 0 or 1, whether you put an edge there or not, to describe a graph. And F to be the set of distinguishers that correspond to cut functions in graphs. And if you do that, what you get out immediately is what's known as the weak regularity lemma for graphs, the Fries-Kanon regularity lemma. It is related to graph theoretic regularity, like Semeretti, but you get this weaker regularity lemma. So it's weaker in what it gives you in the kind of notion of indistinguishability and what it means for really in the notion of indistinguishability, but it's better in that here we have a much better dependence on epsilon, not this tower anymore. We have power 1 over epsilon in the way I've stated it, and then when you do this translation to Fries-Kanon, you maybe get an exponential of 1 over epsilon, but you don't get a tower of 1 over epsilon. But once we see that, so we think of this as really an analog of the weak regularity lemma, so let me call it the complexity theoretic weak regularity lemma. Now you might wonder, is there a complexity theoretic analog of the strong regularity lemma? And as I said, I think for me at least, and it possibly kind of all of us, the tower behavior was a psychological barrier that maybe made us kind of assume there couldn't be a complexity theoretic analog, a useful complexity theoretic analog. And so what I want to tell you about is that I think multicalibration is this new concept of multicalibration that's come out over the last few years, maybe is that analog, and it doesn't have a tower in it. Okay, so This is a reformulation of the multicalibration, I'll say some of the history later, of the multicalibration theorem of Herbert Johnson, Kim, Reingold, and Rothblum, introduced for like completely different motivations that I will also, algorithmic fairness that I'll talk about later. And so let me state it. So I have an arbitrary function. Now I'm thinking of just g as a possibly randomized function, not the fractional function. I have some distribution just like before. I have a size parameter, an epsilon. And now I say there is a partition of the domain of 0, 1 to the n into k or k plus 1 parts, 0 to k. Now k is only order 1 over epsilon. It's not a tower. Such that, and I'll draw a picture that'll make help in a moment. On each of the parts 1 to k, g looks like a random function, meaning on part pi, if I condition on being in part pi, and I look at the joint distribution of x, g of x, it's epsilon indistinguishable from I pick a random element of x conditioned on being in the part, and then I just toss a biased coin with some parameter mu I. And that parameter mu I is just the expectation of g on that part. Okay, so on each part, g just looks like a random function, possibly biased, according to the expectation of g. And it's epsilon indistinguishable by size S circuits. The second condition, or as I only said this for parts 1 to k, and I have k plus 1 parts. There's some exception. P0 is like an exceptional part of where things don't work well. That has just at most epsilon density. And then what is the easiness? In addition to there being few parts, we have that the partition is actually efficiently computable. So there's a function that goes from the domain to 0 to k that's computable by a circuit of size s times poly 1 over epsilon that tells me which part I'm in. So I given an input in small circuit complexity, I can tell you I'm in part I, part 5, part 3. Okay, so in a picture, so I have my arbitrary function g. There exists a partition of the domain. So I get this partition. And then on each piece, I just say, okay, what's the expectation? What's the proportion of ones in this port? What's the proportion of ones in this part? And so on. And on this part, G will be indistinguishable from a biased coin with heads probability, with 1 probability 0.2, here with 1's probability 0.4, and so on. All right, so let's look at, this really is a lot more Semiretti-like. The ways in which it's similar, on each part, we have epsilon indistinguishability we went from random graph of some density mu ij to random function of expectation some mu I. And then we had the exceptional part, and that's analogous to this all but epsilon fraction of pairs in Semiretti. What's the ways in which it's, so those are the things that are similar. What's the ways in which it's different? That's what I'm putting in orange here. One is that our number of parts is only on the order of 1 over epsilon, not a tower. And the second is what do we mean by the partition being simple? Low complexity. For us, it means there's a low complexity function that given an input tells you which piece you're in. Low complexity size s times poly 1 over epsilon. Or if you formulate it using an arbitrary class of distinguishers like I did before, script f, it'll similarly be some combination of a small number of functions from that, poly 1 over epsilon functions from that class of distinguishers by a combining function that also can be done by a circuit of size poly 1 over epsilon. So this is just like kind of like the easiness in the weak regularity lemma before. Whereas in Semiretti, we have the tower, and then here the important thing is notice an important difference, which I wouldn't have thought was important, but it's actually the crucial difference. We're talking about the graph kind of on edge space, But what we have is a partition of vertex space. And then we get from that an induced partition of the edge space by looking at Vi cross Vj. And it turns out that is what forces this tower behavior in Semereti. And why we can have this complexity theoretic version that doesn't have this tower behavior. Okay, so all right, let's do a little bit more interpretation also to see where this came from in algorithmic fairness. So to relate it to the weak regularity, how can we get a, so remember in weak regularity, go back a few slides. We have this function h that's computable by a small circuit that's indistinguishable globally. I'm not talking about on each piece. Well, how do we get that from this multicalibration theorem? Well, what's the function that G is globally indistinguishable from? It's the function that, given x, I first use my circuit little p to figure out which piece of the partition I'm in, and then I toss a coin, a Bernoulli, with probability mu of that piece. Okay? Or if I want to write it in fractional terms, which I'll just do momentarily for one slide to talk about the original motivation for this, I output the number mu sub p of x. And this is a function that's computable by a circuit of size s times poly 1 over epsilon. The work is really just done by figuring out which piece of the partition, and then you can just hard code for each of the pieces of the partition which mu value you want. And it's 2 epsilon indistinguishable from G. You get epsilon from condition 1, and then epsilon for the portion, the exceptional alphas, P0 portion that we threw out. All right, so the original motivation for this was in the context of algorithmic fairness. They were thinking of h of x in the work of Everett Johnson et al. As some predictor that you get from a machine learning model. And they want to have some definition of what it means for that predictor to be fair. Think of it like it's a model for the probability. So machine learning models don't just give you Boolean predictions. They actually typically give you a probability that I think the answer is 1 with this probability. And so it might be like the probability that you think that X will repay a loan, and then you're going to give loans or not based on what this predictor tells you. Clearly want something to be fair and not biased against different demographic groups. And what multi-calibration tells you says, even if I condition on what the predictor says, so the predictor says 0.2, and now I condition on that answer. So I'm conditioned on this set here. My predictor H should be indistinguishable from G, where G is the ground truth. Like what's the actual probabilities that people repay their loans. Okay? And this indistinguishability, they think of their family of distinguishers as kind of built up from the subgroups of the population that you want to predict. So you may have one based on socioeconomic class, maybe some features in X. Race might be another features in X. And then you say, okay, anything I can compute by small circuits on top of these also, I want to kind of be treating all of the groups that you can form in that way in approximately the same way, and that's captured by this indistinguishability condition. Okay, so that's where this came from, why they were looking at it. Just some history. So they didn't phrase things in terms of partition. They phrased things in terms of this conditioning on outputs of your predictor. This partition-based formulation came from this later paper of Gopalan et al. And then we did some additional little bit of reformulation to make it most convenient for the complexity theoretic applications. I should mention, this is a very nice paper of Skorsky prior to multicalibration, giving a complexity theoretic proof of Semereti's original strong regularity lemma, and kind of suggesting, well, maybe there's more of a connection between strong regularity and the weak regularity and the complexity theoretic things than we suspected, but somehow I didn't pick up on that possibility at the time. Then I was really surprised in this concurrent work of Dwork, Lee, Lin, and Tankala. What their work essentially shows is that multi-calibration, the indistinguishability requirement is really the same as the one in Semeretti's strong regularity lemma. And at first it seemed like contradictory to me. Like I thought the tower is necessary in Semeretti. Multi-calibration has a polynomial dependence on epsilon. How could it be the same indistinguishability condition? And it turns out it's because of the other condition, that the fact that in Semeretti it's induced by a vertex partition that creates the tower. And then the kind of work that I'm talking about is coming out of joint work with Silvia Cascoberta, who was an undergrad at Harvard at the time, and Cynthia Dwork. And kind of what we did was realize and show the usefulness of multi-calibration for complexity applications, complexity in crypto applications. So let me tell you a little bit about that. The point here is multi-calibration, like Semeretti, gives you this like small collection of numbers, these mu's, which is the expectation of G on each of the pieces. And then the other thing that's important are the alphas, is like how big is each piece. That's also important quantitatively. Like clearly you care more about the bigger pieces than the small ones. And my claim is that lots of things we want to know about G, its complexity, can be read off from these numbers. So let's think about, suppose I'm trying to just predict G with the highest success probability. Right? I want to error as rarely as possible. Well, what should I do? I'm given a point. I know that I can efficiently determine which piece of the partition I'm in. Right? That's what condition 3 gives us. So if I'm in a piece where the expectation of G is 0.4, what should I guess? What? Oh, 0.4 is good, but if I want to really maximize the probability that I'm right, what should I guess? 0. I should say just do the majority value, right? And if I'm here where it's 0.9, I should guess 1, right? And I just do according to whichever is the majority. There is Andre, in a couple of slides, there'll be one where you should do what you said. So, and then this turns out to be really exactly right. So what's the failure probability of that? Well, I land in piece I with probability alpha I, and then I make an error on piece I with the probability that's the minimum of mu I and 1 minus mu I. And the indistinguishability condition tells us that the probability I err on computing G is going to be within 2 epsilon of the error that I correctly compute the H, this randomized information theoretic partner of G, and the error that I get that is going to be exactly this. So if every A can succeed with probability much better than what we just suggested on that strategy, and the strategy that we gave that uses the circuit to say, which piece are you in and then guess majority, achieves that delta. So think of epsilon as you take it as negligible or arbitrarily small polynomial. So up to that epsilon, the hardness of G is, and up to this poly 1 over epsilon in the circuit size, is exactly captured by these numbers, alpha and the alphas and the mu's. Similarly, hardcore distributions, for those who know what it is, what the hardcore lemma says is that there's the optimal hardcore lemma of Hollenstein. There's a randomized event. So think of that as like a subset or a distribution that has some density. Now it's 2 delta. That's the factor we didn't know how to get with the weak regularity proof of the hardcore lemma. Such that conditioned on that event, G is very hard on average, like it's half minus negligible hard. All right, I'm paying the square root of epsilon. Again, just for now, think of this as negligible. Delta is non-negligible, epsilon is negligible. I'm not optimizing that we're not trying to optimize that in this talk. That's one of the directions for future work. But this is what the hardcore lemma says. There's some event, some kind of think subset of the universe where of density 2 delta where G is extremely hard on average. And it's the same delta as we captured before. And what the hardcore lemma says, the hardness of prediction implies the existence of such a hardcore set. All right, how do you get that extremely easily from multicalibration? Well, suppose I want to make G, like G being very hard on average means being indistinguishable from a 50-50 coin, right? We know that by kind of Yao's pseudo-randomness versus unpredictability. So what should we do? Well, we should just adjust our distribution to make all of these mu's 50-50. So here, like where it was 0.4, I make the ones, I put a little more probability mass on the ones so that it becomes 50-50 unbiased. Here, you know, I have to do a lot of probability mass on the zeros because it was 0.9 to make it 50-50. But I do that on each piece. That gives me a hardcore distribution, like you can think of it as a kind of a probabilistic event on X that has density or probability 2 delta. And so the hardcore lemma just falls out like that. Similarly, if you're interested in pseudo-average min entropy of G of X given X, all right, so if you're not familiar with that, it's just a measure of how much min entropy there is in G of X conditional on X. Well, it turns out that the distribution of maximal pseudo-average min entropy that's indistinguishable from G of X given X is the one given by this information theoretic counterpart, this one where you do these Bernoullis on each piece of the partition, up to, again, a plus or minus epsilon negligibles, and up to poly 1 over epsilon in the circuit size. And we can calculate this average min entropy very easily. It's just log of 1 over 1 minus that same delta that we saw before, which is just the information theoretic hardness of predicting the Bernoulli given X. All right, so at this point, you might say, well, sure, okay, this multicalibration is giving us all these things that involve this same, basically allowing us to reason about this quantity, this sum of alpha. What about some other things that aren't kind of equivalent to that quantity? You could also ask about pseudo-Shannon entropy of G of X given X, which is something that came up in this line of work on pseudo-random generators from one-way functions, so connecting to the black box separations part of the slide of the talk, in my construction with Colin Zhang, where one of the features is that you don't use hardcore bits anywhere. There's no Goldreich-Levin. You find pseudo-entropy and then convert that to pseudo-randomness. You find pseudo-entropy just directly in the bits of a one-way function. And the main thing we needed to characterize was this pseudo-Shannon entropy of a function, say a binary function given, a randomized function given X. And again, it turns out that's given exactly just by calculating the Shannon entropy of this Bernoulli function that G is indistinguishable from. And you just calculate it, and it's alpha I and times the binary entropy of mu I. The thing that this is equivalent to is one where you use a strategy like what you were saying. All right. So let me just spend 5 minutes on a newer set of applications. There's just 2 slides. What about, this is about like computing a function. What about indistinguishability between distributions? So let's say I have x0 and x1 that are only like weakly indistinguishable. And I want to like understand and characterize that indistinguishability and be able to reason about what happens when I take multiple samples. How do we apply multicalibration to that setting? So what distribution, because I have 2 distributions here, and what function? Well, you just do the kind of natural thing in the that we do when we want to characterize indistinguishability as a game. You toss a coin, a uniform coin, and then you sample randomly from x0 or x1 according to that coin. Right? And so just x will be this distribution you get, that's the half x0 and half probability x1, and then b, g of x gives you the conditional probability of the value of that bit b that you chose given that. You apply multicalibration to that pair, that X and that G. You get a partition of the domain. Now, I want to get some information theoretic counterpart of for my distinguishing problem. What I'm going to do is I'm just going to replace on each piece of the partition, I will replace x0 and x1 with their mixture, say the x given conditioned on that piece of the partition. That should be sub pi, x sub pi. All right? So what this is making is so that on each piece of the partition, this x0 tilde and x1 tilde are identical. So the only way you can tell them apart is by looking at what piece of the partition you're in. And their distributions on which piece of the partition you're in are going to be the information you use to distinguish. All right, and so you can argue, using the multicalibration, that x0 tilde is computationally indistinguishable from x0, x1 tilde is computationally indistinguishable from x1, and the optimal distinguisher between x0 tilde and x1 tilde, the optimal information theoretically optimal, can actually be done by a circuit of size s times poly 1 over epsilon. Basically, any distinguisher you want, you just compute what piece of the partition you're in, and if x0 is more likely to be in that piece, you would think it's x0. If x1 is more likely to be in that piece, you say x1. All right. So again, there's just these like 2k numbers that kind of are giving you like the information about the indistinguishability of x0 and x1. And so what do you get from this? So you get these x0 tilde and x1 tilde that are indistinguishable. They also are capturing the indistinguishability under many samples. So if I take k samples, I can't do better distinguishing those than I can with the total variation distance between the information theoretic counterparts up to a negligible additive term. But I also can do that well. So because, again, like just using what the fact that you have a partition into a small number of pieces and I can efficiently tell which pieces I'm in, I can distinguish x0 and x1 with k samples with this information theoretic distinguishability of x0 tilde and x1 tilde on k samples by a slightly bigger circuit. All right, and so some consequences we get kind of immediately as a corollary, a result of Geyer from a couple of years ago that says that if I have two distributions that are delta indistinguishable, then when I look at many samples, I get something that matches what happens with total variation distance. So Geyer did sort of like a direct proof of this. Here, we are able to derive this computational statement just from the information theoretic statement that total variation distance behaves that way. I apply that to the x0 tilde and x1 tilde. And then it's also known in the information theoretic setting that Hellinger distance is, if it's another measure, different than total variation distance, is the right one for capturing up to a constant factor how many samples you need to distinguish with constant advantage. And so we derive as a corollary that the number of samples you need to computationally distinguish x0 and x1 with constant advantage, it's captured by a constant factor up to what we call the pseudo-Hellinger distance. They're indistinguishable from distributions at some Hellinger distance. And if one of the distributions is uniform, turns out you can do this without keeping the x1 tilde to be uniform. This pseudo-Hellinger distance is also captured by the pseudo-Renyi half entropy for those who are interested in Renyi entropies. All right, so let me finish with saying multicalibration, or I would call it strong complexity theoretic regularity, is a powerful tool, reasoning about computational hardness and indistinguishability. Hopefully I've convinced you that. What it really allows us to do is reduce a lot of computational questions just to the information theoretic analog. Some directions find more applications. Another one I mentioned about, talked about a little bit earlier about binary leakage versus leaking logarithmically many bits. So this has to do with also the fact, so right now, I don't think we know the right multicalibration theorem for non-Boolean functions. Like what's even the right statement that's good for complexity and crypto applications. And current versions, we incur a loss that's exponential in L, which would be doubly exponential in the number of bits in the output. And so that's an exponential worse than we would like. Another is I said I was being sloppy with the epsilons, negligible pay poly 1 over epsilon. I think in crypto applications, we want to optimize the concrete security. I haven't opened up the proof of the MC theorem, multi-calibration theorem, to try to do that, or even figured out what formulation is exactly the right version to get the best results for the crypto applications. I think it's conceivable there should be a uniform complexity analog of it, but requires some work to formulate and to prove it. Right now, everything was with just circuits. And then finally, hopefully, and Ron mentioned this, you see what's happening here. That first paper on multi-calibration is published in a machine learning conference, right? It's coming from a completely different motivation, of course, by people who are also complexity theorists. And I think it's really important that we keep this flow of ideas going. It's been extremely fruitful, certainly for complexity theory, I think for cryptography. This flow of ideas going between different areas. And so reflecting on the business meeting yesterday, as we think about what to do as there are more and more papers that hard to fit into TCC, maybe an approach to think is, can we create more opportunities where TCC community is getting together with some of the adjacent communities and create venues that might be a good place for some of those papers to keep this flow of ideas going. And then finally, of course, as you can see, most of this talk was really about trying to realize kind of a vision that Luca had in this line of research. And I think with the Young Researcher Award being named after Luca, hopefully it'll help keep us all continue to be inspired by Luca.
So syntactic question, any of those, like the strong, I guess, multi-calibration theorem, would they improve any of the results in either leakage resilient crypto or in more recently this auxiliary input random oracle simulations? I don't know if you know this line of work, but yeah, this is the previous results were used there.
Have not looked into it at all. And I suspect, so that's one of the reasons I wanted to give this talk here. I hope that some of you who are more on top of these things and know where the interesting questions are might find some of those applications. I suspect, as is, if you want to optimize the concrete security, like the dependence on epsilon in the reductions, you're not going to get it just using off the shelf like what we have in the way we formulate the MC theorem. One has to work a bit to even just get the right optimized version of it for those applications. But I think that would be a very valuable endeavor, because I think if we do have that, it does seem like it would be a big hammer that allows us to tackle a lot of other questions fairly quickly. And then, yeah, certainly if you look at more bits of leakage, as I said, there's things are even worse right now with the multi-calibration.
Only because yesterday we had an invited talk on meta-complexity. I was wondering, because there seems to be a little bit of a connection if you think of this function g as this partition tells you something about g, and maybe if g is simple enough, it tells you how to represent it more compactly. So I was wondering, is that something that's been studied and looked at, and do you think about meta-complexity in terms of this approach, or is it totally disconnected and foreign?
It's a great question. I hadn't thought about it. So I think maybe it relates a little bit also to this kind of question of a uniform complexity analog. So we get this compact description, but right now we get it, at least the way I'm doing it, it's just existential. It's coming from some somewhat non-constructive or min-max kind of reasoning. The way that the multi-calibration theorem was actually proven, though, is more algorithmic. It's using some online learning methods. Boosting via branching programs is like one of the ways they do it. And so it's a very interesting question. Maybe your idea means that algorithm has some sort of meta complexity interpretation as finding some kind of low complexity, I mean, it's a low complexity approximator, so that's a little bit different, I think, than normally what people look at in meta complexity, which is finding a low complexity thing that's exactly the same as the function or truth table that you're starting with. But yeah, very interesting.
So you mentioned you can use multicalibration to reprove your result, construct PRG from one-way function. Do you think there's a hope to use this to improve that result? Or is more about clean up, or so actually you think there's hope to get a better bound using this approach?
Right now I don't see a direction to use it to, I mean, it doesn't seem on the surface to be getting at what the main barrier there is, which is this conversion from kind of Shannon entropy to min entropy. I wouldn't rule it out, but I don't see like a direct way to use multi-calibration there. But maybe, I mean, now we think have this. I guess the problem is that barrier's there even in the information theoretic setting. The cost of converting Shannon entropy to min entropy. What multi-calibration is doing is providing us a tool to reduce computational questions to the information theoretic questions.
As we increase the size parameter, is there sort of any structure to how the parts subdivide or something interesting like that?
Good question. So I guess you're asking a question about opening up the proof of these things. So I mean, at a high level, the way the proofs of these kind of results go is you start out with a trivial partition. Everything is one. You say, okay, now if my indistinguishability condition is violated, let me take a distinguisher, F1, and somehow use it to refine my partition in some way that I'm making progress. And then I keep repeating, and of course, the challenge here is how do you keep things from exploding? And that's kind of, for me, kind of remarkable in multi-calibration. You don't actually just refine the partition, you also merge pieces to keep things from getting cut up too finely. So maybe one can think about doing things that are kind of consistent across sizes, that if you do this in a way where you start with your smallest circuit, you always take your smallest distinguisher at each step, then maybe you can say something about your partition for larger circuits having some relation to your partition for smaller ones, but I'm not sure. And the fact that you do merging may complicate things.
Thank you.
Right. Thanks, everyone.